You're touching the one. Yeah.
All right, thank you, everybody. We're getting ready to start. It's a real treat when we have one of our own super nominated on the research. So I'm very happy that today's person meeting is going to talk to us about fantastic emerging orders and where to find them. So I don't know how much time you want to spend on talking about all of the accolades that Ming has accumulated since 2019 when she started to rise, but I have to mention just a few. And before I do that, I want to say, who knows, maybe 3 years down the road, hopefully not too many, we'll be standing here talking about another rice affiliate celebrating the Nobel Prize. I'm sure that all of you have heard about today's Nobel Prize, right? So, no pressure. We came in January 2019 from Berkeley, where she was a school with Bob Birchall, and that followed her PhD work in Stanford with Stanford, and she's been working on art as all this time, and I guess that's one of the work that she's going to talk about today. And she's been recognized with numerous awards from before she graduated at PhD with outstanding thesis as an educational award, and she was one of the members of the delegation to meet with the Nobel laureate. And then she received a fellowship the L'Oreal Fellowship for Women in Science. And then maybe I'll mention just a couple of awards that she's received since coming to Rice. Within the span of a year or a year and a half, she's had about the Sloan Fellowship. She was named Award Emerging Ethics Investigator. She received the Early Career Award and a couple of others, with very recently the Artist Outstanding Young Researcher Award. I think I'm going to give the floor to Ming and let her tell us about the research. Thank you.
Thank you so much for moving on. I hope this is on. Thank you all for coming. So it's been a couple years since I last up here and did this talk. And so I've actually looked back to look at my slides from 2017. And this is the title I had back then. It's for the quite a number of reasons why this was referred. I talked about fantastic emergent orders and where to find them. So it's been a couple years, and a lot of things have happened, and new fields have emerged. So back here, updating a little bit of all we're working on. So today, I'm going to tell you about fantastic platforms and where to find them. This is the emerging field that we're very interested to work on. And I also engineered this title slide this way so that if you remember nothing else from this talk, I hope you will go away remembering this is one of those fantastic talks. So okay, that aside, let me start with this slide, which I hope most of us as physicists appreciate, because this is really a critical theme for physics, is that we notice that around us in our society there is this emergence, which according to Wikipedia is defined as emergence occurs when the whole is greater than the sum of the parts, meaning that the whole has properties that parts do not have, and these properties come about because of interaction among the parts. And, as people live in this way, you can see these patterns running around us. For example, this is the wave. I think we all know that. So this is election trends over time, and you can see like puddles and blue and red changing over. And then this is also traffic, right? Hopefully on the planet. And the reason I'm showing you three is because actually this is exactly what also happens in quantum material. Individual particles that are going around on the lattice. And their analogies are shown here. So you can imagine that if there's interaction among the electrons in a material, there are certain materials where you can form spontaneous waves in charge density, which is called charge density wave. And you can also imagine there are materials where its resistivity changes like orders of magnitude, and those are called transitions. And then this is a property that is analogous to this thing called spin momentum blocking, which is basically the certain materials, the electron's direction in which they travel is dominant, is determined by their spin direction. Right? So you can see, right, we're fascinated by quantum materials because we're all very interested in this emergence, which appears because of this interactions among the parts. So just to illustrate further what I actually mean by that, I'm showing you a side-by-side picture of this and this. And on the right-hand side here, this is an example of a material that's called manganite. And this is one of these materials where it's the viscosity, which is shown on the right, on the vertical axis. You can see this is plotted on the log scale. Under a certain tuning notch, in this case, in the magnetic field, the viscosity actually can change by 4 orders of magnitude, which is tremendous, right? So this is what you would measure if you gave up one of these crystals and you just put them, I don't know, leaves on the two ends and you measure from one end to the other. But the question is, how does that actually happen, right? So on the right-hand side, this is an example of a real space scanning. So this is what you will see if you take a probe and you scan in real space, pixel by pixel, the local conductivity, and you can see that actually as the material goes from one end to the other, this occurs in a percolation pathway, which much like this. And we hope in upcoming debate, this condition will not occur, but we will see. So this is an example of analogy of what you can see on a large scale versus all these emergent orders that appear in quantum theory. Okay, great. So, recently, there's a lot of us working with materials, and oftentimes we're asked, what's your ultimate goal? And I think it's fair to say, I think a large number of us have this in mind, which is that the ultimate goal we all dream of is one day we can have what is called material, quantum material by design. What does that mean? It means that suppose I want material to turn these powers that the lasers have, I don't know, turn something from metal to an insulator.
Okay. See if I can check. Please go ahead.
Okay. So, for example, suppose that's the hard part.
Oh, sorry.
That's okay. Yeah, I'll show you that's the hard part. So suppose you want a certain material.
Yeah, that's okay.
I can just hold this. Maybe that'll be better. I think.
Could you?
I think maybe it's not
Could
rubbing
you
on
ask
my.
if there is a sound now?
Can you hear, Evelyn? Okay.
So it was a mic set.
Okay. I'll just hold it. I'll just hold it. Okay. Great. So the important thing is, therefore, we have to have the understanding of the following loop, which is that for the materials that we know and we have and we can make, we have to have this understanding of, given a certain crystal structure, what are the first principle information we can gather? For example, electronic structure, this is where the electronic states are, and then connect this to, therefore, also the next step is to connect this to the emergent properties that affects macroscopic material property like electrical, magnetic, or optical properties, right? And then from this, then we can back out the answer. If we have a very well understanding of this loop, therefore we can hopefully go towards that direction where, suppose somebody asks you to make a material of certain property, what do you have to make to realize that? So that's our ultimate goal, very big goal. And so our group here at Rice works here in this regime. We have a probe, which I'm going to tell you a little bit about, that can measure directly the electronic structure of quantum materials. And then from that measurement, then we can infer its relationship to the fundamental crystal structure, and then also make some understanding of how that affects or relate to the macroscopic electronic and magnetic or optical properties. So how do we do that? Oh yeah, I want to make one point, which is that actually our knowledge of simple materials is already really well for this loop. For example, for simple metals, for silicon, right? Those are really well understood, but this is very challenging for materials where the electron-electron interaction is very strong, and these are so-called strongly correlated electron systems. But these are also the systems where the more exotic properties are supposed to arrive. So this is why we're interested to make progress of this understanding loop in order towards this final goal. Okay, so what do? The main experimental technique that our group works on is called angle resolved photon emission spectroscopy, or we call it ARPES, and it has three main components. We have a sample which sits in the sampling environment that we can engineer ourselves. We shoot photons on it from a certain light source, and then via the photoelectric effect, electrons are ejected out from the sample. And when these electrons are ejected out, they carry with them information of their energy and also momentum, because momentum is basically the direction at which they come out at. And then we have, very importantly, this is the workhorse of our machine, which is called an electron analyzer, and this captures the electrons and then analyzes their momentum and energy information. And from conservation laws of energy and momentum in this photon emission process, we can then back out what is the energy versus momentum information of the state out of which these electrons came out of. And that is a fundamental property of the materials themselves. Okay, so that's basically the gist of the technique. This is what our data looks like. This is real data. So the data comes out in 2D cuts of this thing, and it has an axis of energy versus momentum. It's an intensity plot, and the intensity basically tells us what is the probability of finding an electron at a given momentum at this energy, right? And the way when we measure this is that then we can measure, by moving the sample relative to the analyzer, we can then map out the entire momentum space and then generate this kind of three-dimensional electronic structure information. So fundamentally, the quantity that we measure is this A of k of omega, which is called the single particle spectral function, and this captures this relationship. Okay, so far so good. How do I do it, really? So half of the time, our group members travel to these shared facilities, which are large facilities. And these are the 4 light sources that we travel to in North America. And so these are essentially this advanced light source overlooking the beautiful Bay Area in California by Berkeley. This is the Stanford Synchrotron Radiation Light Source by Stanford. National Synchrotron Light Source is at Brookhaven National Lab on Long Island. You can get a sense of the size of this machine based on this, and this is the Canadian light source. So we travel to these 4 places, and the way they work is that you can imagine if you accelerate electrons really fast around the ring, as we all learn in maybe physics 102 or 112, when you accelerate charged particles, they give off radiation, and we harvest that radiation and use that to shoot on our samples, and therefore to look at the emitted photons, right? Just to show you we really use them. So this is a picture of my group member on their last trip to SSRL before the pandemic shut down. So this is the last trip. And I can assure you this is not a staged picture. And this is always how they work at a beamline when they go away for beam time, which is everybody always look at their computer, analyze data all the time, and then talking happily with each other to analyze data. So this is how they work together. Also, we have a system here at Brockman Hall. So in 380, so we installed this also right before the pandemic shutdown, and this is the analyzer, which sits right here. This is what it looks like now. And just let me guide you through this a little bit. So it's a lot of vacuum chambers. The sample sits here in this chamber. And here are 2 light sources. We have a laser and also a helium lamp. Each of them can give photons onto the sample, and then the electrons will come out from inside this vacuum chamber and then go through the electron analyzer. And this is the first happy group picture we took together after the first installation. So everybody looks a bit older now, and so does the equipment. Here, installed last year is a new MBE system, which is a molecular beam epitaxy, and this allows us to do in situ synthesis of thin films. And from this, we can also then grow our own films and then transfer in situ into the chamber and then measure with our ARPES. So that's a new addition we're very happy about. And so I told you that we measure this quantity, which tells us the electronic state, right? But sometimes this is also known as the electron dispersion. Sometimes people think about ARPAS as just a tool for measuring band structure, but that's not true. If you think about being an electron yourself, when you're zooming around in the sample, any kind of interaction you have with your neighbors, with the lattice, with everybody else that you talk to, that affects the state in which you are in. What that means is that the quantity or the single particle spectral function that we measured, it has imprint of all kinds of interaction that occurs in these materials. So as a demonstration, what that would look like. So here, this is a dispersion of free electrons, assuming no interaction. So this is energy versus momentum, and this is your so-called band. If you think about if the electrons are interacting with some phonons, then that will actually produces a so-called kink in this dispersion. There's an energy scale associated with this. So the electron dispersion from this energy scale to the Fermi level is renormalized. So you can see the slope is reduced, and then there's a larger scattering from above beyond this point, right? So by measuring this quantity, then we can also get information about the interaction strength of the electrons and phonons, and what temperature they onset, and so on and so forth. We're also sensitive to electron-electron interactions, which are shown here. So if the electrons are interacting with each other, they will slow down because they're talking to other people, other electrons. And the effect is that the slowing down is also produced in a normalized slope. So the slope is also smaller. We can also gain spin resolve information. If the electrons carry a certain spin texture, then we can also do that from our ARPAS measurements, right? So you can see there's a lot of information that's actually captured in the single particle spectral function we can measure with our tool. Okay, so I said I'm going to talk about flat bands, and so what is a flat band, and why do we care about them? To make this a little bit more intuitive, imagine, I think we're all used to live in the real space, so that's over here, right? So all there is to flat band is that if you consider two energy scales, you have a Coulomb interaction, that's just the electron-electron interaction, U. We also have the electron hopping, what is the kinetic energy of these electrons. So it's a relative strength of these two energy scales. So on one limit, if the Coulomb interaction is much, much smaller than the hopping, you can imagine in the traffic, you won't see the individual cars, but you see really fast moving things, right? And then on the other extreme, you can imagine a situation where if your cars and our next car are interacting so strongly, there's basically no kinetic energy left, so you end up with this very local picture, right? This is real space. What does that mean when we think about the momentum space, which is where the bands actually live? Imagine this is a simple band of energy versus momentum, right? There are a couple things we can read off of this. I said the slope. This is basically how fast the electrons are traveling, so you can think about this as, right, essentially like a velocity. And then the energy window from which the band lives, this is essentially the bandwidth, and that you can think about as basically this hopping. So if you go to this regime where the interaction is so strong that things are slowing down, what are you going to see from ARPAS spectra or band dispersions? You're going to see the bandwidth being reduced, right? The slope being reduced. So slowly this band is going to be sort of squeezed and flattened against this Fermi level. And then eventually when you reach the point where there's no more motion, where everything is local, and that means in momentum space, this becomes a completely flat thing, and that is called a flat band. Right, so this is a regime where the Coulomb interaction is much, much stronger than the hopping of the electrons. Okay, so intuitively, this is the picture. Do we actually see this kind of thing in real material? And we do. So this is an example of a material we really like, and I grew up with as a graduate student. So this is called one of these iron-based superconductors. And what we found, essentially, is that in this compound, in this material, if you focus your eye on this band, right, this curvy thing, if you dope the system with certain element, from one end to the other, you can sort of see this band start to get flattened as you go towards this direction. And that essentially is a direct evidence that the correlation or electron-electron interaction is becoming stronger as you go from this end to that end, which is exactly described by this process. So in this example, actually, we discovered that if you keep going, you will eventually enter what's called a orbital selective Mott phase, where that band becomes completely localized and flattened, and then it's no longer there. Anyway, this is some of the results that we published last year. So this is what we're looking for. All right. So why do we care about flat bands? And I'm very biased. I only look at things from our own colleagues. So I'm going to show you a couple of examples of why they're interesting. This one is from our own Evelyn, and when she was a graduate student, and this is a very highly cited paper. There are some very exotic states that can be produced in the regime where you have these flat bands. This is her prediction of high temperature fractional quantum Hall states. This is Yonglong's result, where you have he observed experimentally fractional churn insulators in magic angle just by their graphene. And then most recently in bulk materials, this is the result of Timel's group from Lei here, and this is their report of quantum criticality enabled by flat bands in the Kagome lattice. So the bottom line is, when you think about a flat band, it's contributing a large degeneracy across momentum space, which means that it is unstable against many kinds of interactions that will connect this large degeneracy and then lead to emergent orders. So this is a regime that will be very interesting for looking for emergent orders and emergent phenomena. Okay, so the last thing we want to ask is, how do we find them? Where do we find them? I agree that most of the time, where you can find localized traffic depends on how people interact with each other. But there's also some merit in thinking about the fundamental design of the lattice that would produce this kind of localization. And if you've been to Hotel Zaza next door and gone through this circle of death, you can sort of understand what I mean. If we have a design of certain sort, it may lead to certain localization effect. And this is, to some extent, is where we're going with looking for this in quantum materials. Crystal design. So where do we find flat bands? So actually, the important aspect of this is called geometric frustration. So actually, this idea has been around for a long time, and this is especially well known in the field for quantum spin liquid candidates. And the geometric frustration means that you can have certain types of crystal lattices where there is a tremendous amount of frustration. If you consider, for example, spins on each of these atomic lattice sites, suppose this one is up, this one is down, and the third one will be very frustrated, not knowing whether it should be up or down, right? So this kind of frustration for this interaction limit produces candidates for quantum spin liquids. In the recent couple of years, this idea has been, before I do that, let me say a few words. So this is called a triangular lattice. This is a Kagome lattice, and this is the pyrocore lattice. And let me just introduce a little bit this perhaps the most well-known lattice in the recent years. And this Kagome lattice is made of this corner sharing triangles, and the name comes from this basket weaving pattern that's often found in Asian lanterns and so on and so forth, right? And okay, oops. I think somebody liked this so much they drew on it. Okay, I don't know how to clear that, but anyway, I won't. Please don't be bothered by that additional remark. Okay, so Kagome lattice has become one of the favorite lattices for a lot of experimentalists and theorists, I guess. So this is an example of a Kagome optical lattice constructed. And in real quantum materials that you can synthesize in your labs, there are also many candidates that have these repeating units of a Kagome lattice. This is an example. This is what how it looks like in a real compound, right? So this geometric frustration, recently people have realized that this geometric frustration can also be a mechanism to produce electronic flat bands. And let me just illustrate that really quickly here. So here's our lattice. It turns out that there's an exact cancellation of the nearest neighbor hopping, such that there is no hopping out of these hexagons, such that the electronic wave function is localized within each of these sites. If it's localized in space, and you think about the momentum space, this means no hopping So no kinetic energy is quenched, so you have a flat band that is flat everywhere in momentum space. And this kind of construction is not unique to Kagome lattices. It is general to any kind of line graph lattice. And so besides Kagome lattices, there are actually many of these given to us by nature in many of the compounds that we actually have and work with. This is an example. There are two papers that have come out that has gone through all the crystals that's available and look at what are the most popular or most commonly occurring crystal lattice motifs that will give you this kind of geometric frustrated flat bands. And so these are the top 5 contenders. You have the Kagome lattice, empire core, and so on and so forth. You can see each of them, the band structure, you have a flat band in all of them, right? So this is basically where we can find candidates for such kind of flat bands. Okay, here is the actual talk. So I'm actually today show you our group's recent efforts in looking at 2 of these lattices. In 2 dimensions, I'll show you some results that we have made in 2D Kagome lattices, and then show you another compound, which is of the 3-dimensional version, which is the pyrocore lattice. So let me first talk about the Kagome lattice. I gave you the sort of a brief overview of what that looks like. Let me just make the following couple key points. If you take any Kagome lattice and you look at its band structure, there are 3 important signatures that is always there in this band structure. So let me illustrate that. I keep pointing at this. Maybe some of us are not so used to look at this. You can imagine this is your real space. If you cut your crystal down and you really look at it with a very fine microscope, eventually you will see this in real space, right? But where band structure lives in momentum space, and this is the unit, repeating unit in momentum space, which is the Brownian zone. So the way we represent this is by drawing the band dispersions on a pathway. So this is gamma point to K point to M point back to gamma, right? So this shows you there are 3 bands, and you can see how they go around, right? This is the real 3-dimensional band structure, and the 3 key signatures are the following. First of all, we have the flat band, which you can see here. This is the flat band, which is flat everywhere in momentum space. And if you tune your chemical potential to close to this flat band, to add the flat band, then there is a Stoner instability that will lead to itinerant ferromagnetism, at least according to the theory. Second is that there's always a band crossing here at the K point, right? This is K point in the Brownian zone. And so just 2 bands crossing without opening any gap. This is called a Dirac cone. And if you tune your Fermi level to here, and if there's also spin-work coupling, that will actually give you finite barrier curvature and give you an Ohm's Hall, but I won't actually talk about this today. The third one, which is actually really important and which has really captured the heart of many people in the recent years, is this object, which I circled in blue here, and which is essentially a saddle point, and it's also called the Van Hove singularity. It's a saddle point because you can see the band curvature is down and up along 2 different pathways, which means that this looks like a saddle, and in 2D limit, the density of state will give a divergence at this energy. And it turns out, if you tune your chemical potential to one of these Van Hove singularities, which is the case here, you get a very special Fermi surface. This is plotted in 2D. It looks like this hexagon, and from this, you see there are 3 pairs of parallel sections of the Fermi surface which are connected by the same wave vector, and this will give you instability, which is called a charge density wave that will actually fold the Brownian zone and produce a wave in the density. We sort of talk about this. This is like a stadium wave, right? And so these are the predictions of a 2-dimensional Kagome lattice. So, okay. So actually, there are many Kagome lattice materials people have looked at in the recent years, and from this very simple, maybe half naive correlation of these electronic structure features and their material property, then it's not hard to see that the materials, don't worry about what they are, but just largely look at this. They can be grouped into 2 parts, right? You have materials that only exhibit charge density wave but no magnetism, or you have materials that only live in the magnetic sphere but no CW. Why is that? In a very simple, naive picture, maybe it's the following. So for the material that have magnetic order, they typically have the flat bands to be where the chemical potential is. For example, this is the compound of iron tin, and iron tin is known to have a magnetic order such that the system orders magnetic around 400K. And according to the calculation, you can see this is actually where the flat bands live near the Fermi level. So this is one class of materials that exhibit magnetism. Or you can have systems that exhibit a charge density wave, and these materials, such as this one, actually has a measured Fermi surface that very much resembles what you expect when the chemical potential is actually at the Van Hove point. So here, this compound, this material, AVS for short, has been confirmed experimentally to exhibit this charge density wave. You can see that this is a real space scanning tunneling microscopy image. You can see the wave in this real space, and that is consistent with the theoretical prediction of the nesting between the parallel sheets of Fermi surfaces that give you this 2x2 CW order, right? So this is kind of naive, but at least it's consistent with this understanding. Maybe it's not so hard to understand why they are so divided, because if you look at this picture, the Fermi level is either near the Van Hove or near the flat band, but it's very hard to engineer one where it's near both, right? This is why it was very surprising, actually, last year, 2 years ago, Peng Cheng's group actually discovered here there's a compound that actually exhibits both a charge density wave and a magnetic order in this overlapping region. And this is a compound, this is a story I'm going to tell you about because we work on this together. So iron germanium structurally is very simple. It's been around actually for a very long time, almost 40 years. And what was known about it before is that if you look at the crystal structure, the iron, the red balls of the iron, and they make these Kagome lattice, and they're stacked along the c-axis, right? So it was known already that below 410 Kelvin, if you cool below here, the moments actually become ordered on the iron lattice. They're ordered such that they all point in the same way within one sheet, and then they all flip over on the next sheet, and then this repeats, right? So if you think about what you expect, this is real space. In reciprocal space, you can think about the Fourier transform of this, right? So what this means is that unit cell actually doubles along this axis. So what that means is that in reciprocal space, if you do diffraction, you would expect to see peaks that appear between the lattice peaks. And so Peng Cheng's group and our shared student Xiaokun did neutron scattering here, and this is exactly what they saw, right? So you can see these are the black peaks you can see from the lattice, and then as you cool down below 410 Kelvin, you can see additional antiferromagnetic point diffraction peaks that appear. Fine, this is great. But they just had to cool down, and when they did, across 100K, they saw all of these interesting new peaks that appear. This was actually a very surprising finding because they were not expecting it. So you can see here, there's all these additional peaks that appear, and they can analyze the intensity. I won't go into the detail, but they can conclude that this is actually, these are not magnetic peaks, they're structural peaks, and this is the discovery of this 2x2 charge density wave in iron germanium. And this is very strange. This is not expected because there are very few examples of materials where you can have a CEW order that appears well within the magnetic order phase. This is very rare. So then we went through a lot of collaborators to check for this CEW order by different probes. This is one of the first ones. We collaborated with Princeton group to look at real space. Can they actually confirm there's a real space charge density wave? They can. And so this is the STM scanning tunneling microscopy image. And they can see that when they take the Fourier transform of this, they can see the 2x2 peaks appearing in this. So there is indeed a charge density wave order from STM. And you can see a gap developing in the density of states. And also, if you have a phase transition, you better have some sort of signature in your heat capacity. So here, this is heat capacity measurement showing a phase transition around 100 Kelvin, which confirms the CW order. There's also signatures in the first derivative of the resistivity, shown here, and also magnetic susceptibility, and so on and so forth. So this really confirmed from many different techniques that this is real CW order. And since then, there's actually been a lot of activities in the community looking at this. So these are all the papers I put out of the archive this morning on iron germanium since the first paper appeared. And you can see this is a mixture of theory, experimental results. There are many more puzzles about this compound that we haven't resolved yet. So we're very interested in this material to understand these mysteries. Why am I here talking about this material? It's because of this question I posed earlier, right? if you think about this understanding of this band structure associated with each of these features, how in the world do you get something in here, an overlap region between these two? So that's what we hope to provide information on using ARPA as a look at the single particle spectral function. So in order to understand that, I want to first show you maybe the simpler picture of this from the theory, and then show you the data after that. It's easier to understand this from a theory perspective, from the illustration based on the theory. We collaborate with Binghai Yen's group from Weizmann in Israel. They carry out first principle calculations, or density functional theory calculations. And here's what they find. So if you look at the density of states, right, this is the electronic density of states. If they calculate this for the non-magnetic material, for the non-magnetic phase, they see a really large peak here at the Fermi level. And then when they calculate that for the AFM phase, they can see the peak splits to 2, right? How do you understand that? It turns out that peak corresponds to a large a flat band in that region. So this is the angle resolved or momentum dependent density of states or band dispersion. And you can see that this bunch of flat bands actually correspond to this peak in the paramagnetic non-magnetic calculation. And then when you lower into the AFM order, it's split to 2. How do you understand that? Well, if you take this crystal structure, you think about each layer. Each layer is ferromagnetic. What does that mean? Let me illustrate this with a simpler picture. So here, this is a tight binding calculation. If you're high above the magnetic order phase, you will see that each state has a mixture of spin up, spin down, that those states have the same energy. But if if the spins become ordered, then the spin up and spin down states can no longer be degenerate. So what happens is then you can have a splitting of the bands going up and down, right? So the end result is that because of the magnetic order, there's these Van Hoff singularities that used to be far away from the Fermi level that gets shifted towards the Fermi level, eventually landing there. And then that's where we can also have the presence of the charge density wave order. This is what we can also observe experimentally. So this is data collected by Xiaokun and also our postdoc Jisop. And so here, let me guide you through this. The way to read this is the energy versus momentum data, raw data. And this is the constructed three-dimensional view of this. So this is energy, and this is Kx and Ky. First of all, we can see the direct crossings here from the series of circles that shrink down and then expand out. Right? And that matches the prediction of this direct crossing of the K point. Also, they can also see that when this goes up, they actually meet at the end point in the Brillouin zone and forming this expected Van Hoff singularity point, right? But how do we actually show this is the Van Hoff singularity point? We have to do some more to show that. Imagine if doing the following. If we take a cut along this zone boundary, right, what do we expect? A saddle point is one that looks like a Pringle chip. It's a saddle, right? So it should be curved down in one direction and curved up along the other direction. So if you look along the zone boundary, you can see that this is a hole-like band. And we can track where the band top is. And if you walk in parallel to the left and to the right, you can track where that band top is. And you can see that while it's pointing down in this direction, in the perpendicular direction, it actually points up. So this demonstrates that this band dispersion actually does follow the shape of the saddle point. So therefore, this is indeed a saddle point. So that matches what's expected here. And also, we have done temperature-dependent evolution of this. We can measure the Van Hoff point as a function of temperature. We can see that it shifts as expected across temperature. And this is the shift of the band. And this is the ordering of the moment. We can see that this picture is at least to the zeroth order qualitatively correct. Okay. And just to show the ones that want to see the actual curves, we have done very fine temperature dependence. You can see this peak is where this band is as a function of temperature that shifts towards the endpoint. The last bit I want to show about iron germanium is that can we actually see the Van Hoff singularity being participating in this charge density wave order? Oh, wow, okay. And the answer is yes. So the way we can see that is the following. So imagine we take a cut here, which is shown here. We can look at the energy-dependent density of state. So here, this is this EDC or energy distribution curve. And as you go across the CW order, this develops a suppression here. And this is indicating a gap that forms just like as seen in the STM data. right? And we can track the temperature at which this develops, and that is actually happening right at the CW temperature. So therefore, we can actually see that the Van Hoff singularity bands are indeed involved in the CW order as expected. So here, in this example, I've shown you this, information we have gained by looking and measuring at the single particle spectral function. And from this, we can gain understanding that based on this crystal structure, this kind of band structure is actually roughly correct. And from this, we can see that this ferromagnetic Kagome layers spin split the bands, and therefore can actually actively bring the Van Hoff singularities close enough to the Fermi level to eventually enable the formation of this emergent charge density wave order. Right? There are other materials that we have worked on that also belong to this class that I won't talk about. I will try to hurry up a little bit on the last part, which is the three-dimensional version of this. One disadvantage of working with Kagome lattice is the following. I've shown you the picture of a bulk crystal. You can imagine in that crystal, there are many, many of these layers stacked on top of each other. And such that there is a finite interlayer coupling that you cannot avoid, and this will disrupt the destructive interference that will give you this flat bed. So what do? We have to find a way to remove this interlayer coupling. And the way to do that is by going to 3 dimensions and finding materials where the outer plane hopping is also removed because of this quantum interference effect. And that is a pyrocore lattice. So, okay. And the way to see that is the following. If you take a pyrocore lattice, you can cut it in such a way that you can expose a Kagome lattice like this. You can do that in 2 ways. So everything we know about Kagome lattice is still valid in the in-plane direction. But if you actually think about the outer plane hopping and calculate your Wennian amplitude, you will see that the atomic lattice that is actually not contained within this layer has identically 0 amplitude. What does that mean? That means that the electrons cannot hop outside of this between the layers. And this means effectively we have a picture where you can consider the pyrocore lattice as 2 decoupled Kagome planes. And everything we have learned about Kagome lattice still carries over in the formation of these flat bands. And there's some dispersive bands in addition. So qualitatively, we can see this in a real material. And for this material, which is copper, vanadium, 2 sulfur 4, it's a spin-now material. It's actually identified by Chendensetti here. I don't know if he's here, from Tim Yau's group. He was, as a theorist, he went through a lot of materials that actually could potentially give rise to this kind of pyrocore lattice physics and told us that this is the material to look at. This is the best thing that can happen to an experimentalist. So we convinced Peng Tong to grow this material. To make a long story short, we can actually consider this material as dominated by this vanadium sublattice, which is a pyrocore sublattice. And if you look at the density, if you look at the calculation of density states, which was carried out by Boris Jakobsen next door, you can see that indeed the density states is dominated by vanadium near the Fermi level, which means the pyrocore lattice actually dominates the physics in this material. And you can see the large peak, which indicates the flat band. And when they do the DFT calculation, they can indeed see this very flat band. And what's more, indeed, if you do the projections to different orbitals, this is all coming from vanadium T2G, and copper and sulfur actually have very little weight near the Fermi level. This is also great, which means that we can think about the system as basically a pyrocore material. So we went through and did this measurements, and this is done by Jian Wei, who is a postdoc in our group. He really carefully went through a lot of materials to find the best condition to do this measurements. And from what he can see is that if you look at this picture, blue is actually the highest intensity, which means that you can actually have a flat state, basically very, very flat state across the momentum space. You can actually see that in the peak here, right? You can see that both in the in-plane direction and also in the out-plane direction. So this is actually very consistent with having a flat band at the Fermi level. But the problem is, if you go back to the DFT, you remember this flat band, according to this calculation, sits 0.5 millivolts above the Fermi level. So Jian was like, what? Why is that? So we have to think a little bit harder about why experimentally we can see it at the Fermi level. It turns out that this is actually really interesting because this reminded us of the story we work on with the iron-based superconductors, which is that you also have to think about adding correlation effects that were not taken into consideration in the DFT calculation. So Tim Yau's group have done this calculation by carrying out slave spin calculation, and they can see, to make a long story short, by adding Coulomb interactions, they can actually make a better agreement, bring the flat band down to the Fermi level, all the bands are normalized, and actually makes a better agreement with the data that we see. right? So here, to make connections to macroscopic material property, we have also collaborated with Chu's group at Washington. They did the measurement on the resistivity, and they can actually see that as a function of temperature, there's a power law dependence, and this deviates from the t-squared behavior expected for a fermi-liquid behavior. So this suggests that there's non-liquid fermi-liquid behavior, and as well as a large Sommerfeld coefficient, which suggests that the mass is enhanced by a factor of 6 in this material. That is very consistent with our observational flat band at the Fermi level, right? So to make a long story short, this is actually very analogous to some of the heavy fermion systems where you have both the presence of very flat F electrons and dispersive states. But except in this material, it's a pure D electron system, and everything is from d orbitals, except we have a flat band which is produced by both quantum interference effect as well as correlation effect, but it has resistivity behavior, which is reminiscent of that in these heavy fermion systems. Okay. I know I'm running out a little bit of time, so I want to bring you towards the conclusion. So here in the pyrocore system, we again see this from a crystal structure. There's a prediction on where the flat band should be, and by looking at the single particle spectral function, we can actually see a cooperation of this quantum interference effect plus Coulomb interaction working together to first make the flat band and also bring it to the Fermi level, such that there's a direct consequence potentially in understanding why there's these emergent property behaviors in the transport measurements. Okay, so the two examples are here, which demonstrates that these are interesting systems where we can find flat bands that actually have that has a direct connection between the lattice, the geometric frustrated lattices, band structure, and also the emergent properties, including orders and also these nonlinear transport properties. So these are the people for each of these projects. I flashed through all their pictures previously, so I will just take them all here. But just if you be patient with me for 2 more slides. I also want to show you some extensions beyond this, right? So flat band systems is one direction where we're working at. We actually have a couple more directions that our group is interested in working in. So we work more interesting quantum materials that exhibit strong correlations. Magnetism, we have some interesting observations of switchable 2D van der Waals ferromagnets. We also have another direction, which is a very nice collaboration with Emilia's group, and also the theory support from Andre and Matt on different types of nodal line systems. And in terms of instrumentation design, we're also very interested in exploring different ways that we can do in situ tuning. So here are 4. This is a uniaxial string we can apply in situ. We can compress or drag the systems and directly measure arpets and see the changes on band structure directly. This is the in situ surface etching. So this is a bismuth selenide, which is a topological insulator. By reacting chemically on the surface, we can actually see very nice evolution of topological surface states. And then this is a in situ thermomagnetic field that we're developing together with Han Yu's group and also with Jun's group. And this is a very, very exciting direction. We're now starting to see some evidence of direct field effect on band dispersions in these chiral materials. And then finally, this is the MBE system that our postdoc Jung has set up. And we're starting to grow some Kagome thin films. If anybody's interested in collaborating, we're very happy to talk about that. Very last slide. And this is the most important slide. I want to thank all of my group and who have done all the hard work, without whom none of this would have been possible. And thank you all, I guess. Yeah. Right. Yeah, so sorry. Oh, Kaden asked if the resistivity power law is T to the 1.6, whether that's common or not. So that's what I sort of went too quick. So this is actually, thank you for this question. So the plot here is this resistivity exponent n, right? So you can see this is a heavy fermion system, a Kono system, serine-based Kono system. And you can see that 1.6 is yellow regime, right? Which is actually seen in this phase, which is right outside this order phase. So this is the connection that Timel pointed us to, that there's analogy between, perhaps, that what we're seeing is similar, analogous to some of these other Kono systems. Higher core? Yeah. Oh, that's a very good question. We can only resolve one. Yo, sorry, Ben asked, so according to type binding calculation, the higher core there should be two flat bands. Where is the other one? So you can see, I guess this you can only see from DFT. From data, we can only resolve one. From the DFT, there are, I guess, two that are close by. And then for each orbital, you will have a set of two flat bands. But experimentally, we can only resolve one. That we don't know. I mean, it could be that, or because the type binding I showed you is without spin-over coupling. So when you add spin-over coupling, there's actually the two becomes degenerate at other points. Then yeah. So, but experimentally, this one is very close to the flat band. That's the Fermi level, and we can only resolve one. So the answer is we don't know. Yeah. Oh, this is a very good question. So right, so what I showed you is the type binding calculation, right? So in this, oh, sorry, yeah, this is a very good question. Ben asked, is there a flat band in every power core system? And the answer is that in this simplified picture, if you assume there's no hybridization between the power core sublattice and the rest of it, that is likely true. But in this material, I sort of ignore the other stuff here. If you have a strong hybridization between the vanadium sublattice and copper and sulfur, then that will go into destroying that flat band. So yeah, so for this system, if you look at this DFT calculation, this one is relatively flat because there's very little hybridization. Maybe some sulfur comes in, but there's lower hybridization in some other compounds, some of this lava space, for example. There's stronger hybridization. Yeah. Matt? Oh.
So in iron germanium, you show that the Bell singularity first give rise to magnetism and then charge order. Right? And is there any understanding as to why magnetism coming first and
Yeah.
order?
So okay,
Other way around.
let me repeat your last question. So you want to ask whether in iron germanium the Van Hoff singularity gives rise to both magnetism and charge density wave. That's not the intention which I presented. So essentially, if you think about this simple, naive, and likely wrong theoretical picture that you get of magnetic order. So here, the picture from this is naively if you have a type band. Oops. Okay. If you look at this, this flat band naivety will give you the itinerant magnetism. And it turns out, I don't know by coincidence or not, all of these magnetic Kagome systems, if you calculate their band structure in a non-magnetic state, the flat band is always close to the Fermi level. I'm not saying that this is what's actually driving the magnetic order because that's likely not true.
No, but I think the question is, why does magnetism happen first and then charge density wave?
Right. So according to this picture, the reason is because you think about charge order arising out of magnetic order phase, which arises out of the non-magnetic phase. So if you calculate the band dispersions in the non-magnetic state, the flat bands is actually living at the Fermi level. So this picture, right? And then when the magnetic order sets in, you have a set of band, spin up, spin majority, spin minority states that split, right, into this fashion, such that the Van Hove point, which used to be far away, living far away from the Fermi level, now gets lifted up towards the Fermi level. So the Van Hove is there when the CW order sets in.
So it's only because of the splitting caused by magnetism that the
Yeah,
Van Hoff
that's the implication. Yeah.
So, one of the issues that's always coming up with straight metals, things that are not very liquids, is what the relationship is between the electron lifetime and the transport lifetime. Yeah. So, is there a line width? I mean, it's a complicated system, but in this power core system, is there a line width you can try to extract to tell you the electron lifetime?
Yeah, this is a very good question. No, we cannot. So the problem is with the three-dimensional materials, it's very hard to cleave. So it's already very hard to actually resolve the dispersive bands. So the width is not a pure measurement of, I think, the intrinsic lifetime. But that's a good point, yeah.
So, since we're on this slide here, related to Yong's question, if you have Kagome lattice
Are you guaranteed to have it?
First of all, is Kagame guaranteeing the flat band, and what causes the Van Hoff singularity? But let's say that you have a Van Hoff singularity and a flat band. Is there a way to tell a priori how much splitting you're going to get from the magnetic order and whether the Van Hoff is moving in the right direction?
That's a great question. So, so actually for iron germanium, the correlation is not negligible. So if we compare our measured dispersions with this band, there's not a one-on-one matching. So this is only providing some intuitive, qualitative overall picture of what these features do. But that part, there's no, I don't think that's a very accurate prediction of what the band structure would look like given a magnetic Kagome system. I think. The second thing is that this picture, we also recently mentioned iron tin, which is another magnetic Kagome system, but that one does not have a Tardizi wave. So you may ask. Yeah, that's exactly the point. Very good. Yeah, so so that there, when you have the bands that split, somehow the Van Hoff gets destroyed in that process because of hybridization with other bands. So in that system, we don't observe Van Hoff singularities, even if there's magnetic order. In this system, this is preserved in this process, it looks like. Yeah.
But if not, let's thank you again.
Yeah.